In the previous recording, I introduced the way that conservation of energy can be thought of and used with electric forces and hopefully electric fields, and that's part of what's going to happen in the next couple of lectures. The essential idea is that, like any force, the electric force can do work, and work changes the kinetic energy or the potential energy, or both, for a charge. And so I described that conceptually. Now I want to go into it with a bit of mathematics. And once again, we'll start with our simplest possible charge, a positive source charge. And again, I'm going to do things with a negative. Well, no, I think I'm going to change my mind. Let me this time do a positive source charge. I'm sorry, I have a positive source charge. Let me now also use a positive test charge. So to be clear, the thing whose potential energy and kinetic energy and the work done on that we're going to be calculating with is the test charge. So we're going to be calculating the kinetic energy of the test charge, the potential energy and the changes of potential energy of the test charge, the work done on the test charge. And all of these things happen due to the force created by the source charge and ultimately the electric field created by the source charge. Okay, so let's suppose my test charge, call it capital Q here, and our source charge, little q, and they are separated by an initial distance, r0. Pardon me. And as in the introductory lecture on this, we'll assume, at least for the moment, that the charge, we bring it over, we place it there, we hold it for a moment, take a deep breath, its initial velocity is 0, we release it, and it immediately starts experiencing an electric force. In this case, since the two charges have the same sign, or if you prefer, because the electric field points that direction, the test charge will immediately start accelerating away. But I want to talk about it now in terms of energy. Okay, so there'll be a force on the test charge due to the electric field of the source charge. That force will cause the test charge to move, to displace in this direction. So there'll be a force and a displacement. The product of those two things is the work. And let's suppose that eventually we stop the experiment up here, and at this place, the distance of our test charge is now, call it r final. Okay, so the distance that it moved was r final minus r initial. The force that acted on it was the electric force, which we know how to calculate, and so we can easily calculate the work done. So let's see, r initial equal initial distance. Well, let's do this first. So Q is our source charge. Capital Q is our test charge. R naught is initial distance between them. R final is the final, R sub F is the final distance between them. Okay. With all that defined, we can now calculate, to start off with, the work done. Okay, work is, well, you might remember that the expression for calculating the work went from simple to less simple to a lot less simple. Okay, so I'm going to start out with simple, and then we'll get progressively more complicated. So F times delta R. I'm using R, of course, because it's moving in the radial direction. I don't want to use delta X or anything else like that. So the force here is Q times E. The electric field is K times Q, sorry, just Q, little q, Q over R squared. Okay, I'm not going to worry about the direction indicator for now anyway. So the force, you know this one very well, Q over R squared. Okay. And so then the work done then is K times Q over R squared times delta R. But delta R is R final minus R initial. Okay, so that's the calculation so far as it goes. But there is one other issue that we need to deal with. And that is, what does R mean down here in the denominator? I just threw it in there because we're used to it, but let's think about it a little bit. Well, back in the day when I was telling you about electric forces and then electric fields, R was always the distance from the source charge to the point in space where you're calculating the field, or the point in space where you're calculating the force. And that's still sort of true here, but we have to tread a little more carefully. So let's go back to our diagram and think about what we're actually talking about. So little q here is the source of the force. And then capital Q is the test charge, the thing experiencing the force. Sorry, I want to get the camera lined up the way I like it. Okay. So when we're talking about the force, at the beginning of the process, the distance from the source charge to the test charge, the thing experiencing the force, is R0. At the end of things, the distance between the source and the test is R final. So in the denominator, QQ over R squared, R at the beginning of things represents R sub 0. At the end of things, it represents R sub final. So making what is admittedly a hand-waving argument and not a mathematically rigorous proof, I'm going to claim that I can and should write R as the square of R final minus R initial. In other words, the distance that the thing moved. Okay? And if I do that, then as you can see, this factor divides out one of those factors, and the result is the work can be calculated as KQQ over R final minus R initial. Then, if I get lazy, and say, well, I'll understand that the thing in the denominator is the change of position of the test charge as it moves from place to place, from its starting point to its ending point, then let's simply define little r to be that. Okay, now before I go any further, normally I would write this as delta r, but it's traditional in this particular field not to do that. We tend to just write it as r. And the only reason for that is that it keeps the equations from getting unnecessarily cluttered. But you need to remember that r is actually the displacement in this context. Okay, so that gives eventually that the work, it can be calculated as k q q over r, and that's good. So, yeah, this is pretty easy. So just tell me how far the thing moved, tell me how big the two charges are, and I can tell you how much work was done on the test charge when it moved from its starting point to its ending point. So that's work. There's actually three concepts, right? There's work, there's kinetic energy, there's potential energy. And so this is work, and so we'll have another lecture recording on kinetic energy and another one on potential energy. So let's tackle those next.